All right, so today we're tackling a huge topic in medicine, something that's both a massive challenge and, honestly, an incredibly clever solution. We're talking about antiviral drugs, how they work, and how they let us turn the tables on an enemy that literally operates from inside our own bodies.
So let's just start with the central question, right? How do you fight an enemy that hides inside your own cells? See, a virus isn't like bacteria where you could just, go in and attack it directly. No, this thing is a ghost in the machine. It's a hijacker, and it's using your own cellular machinery against you. So how do you stop it? How do you take out the bad guy without burning down the entire house? That's the puzzle we're going to try and solve.
Okay, to really get the solution, first we have to appreciate the problem. We need to understand the virus's own strategy, which is, frankly, brilliant and a little terrifying. The best way to think about it, it's a heist, a cellular heist. So here's what's so wild about a virus. It's not technically alive. Really, you can think of it like a tiny little flash drive. It's got one malicious program on it, and that's it. On its own, it can't do a thing. It's just a little speck of genetic code, either DNA or RNA, wrapped up in a protein coat, just waiting for a chance to plug itself into a living cell.
And this heist, it plays out in four main stages. First up is entry. The virus gets past the cell's security and gets inside. Then, the really crucial part, replication. This is where it hijacks the cell's entire factory floor. It forces the cell to stop doing its normal job and start churning out viral parts instead. Next, assembly. All those new parts get put together, building brand new, complete viruses. And finally, the destructive climax, release. The host cell literally bursts open, unleashing a whole new army of viruses to go and do it all over again.
And that right there, that's the heart of the challenge. The virus isn't just in the cell, it weaves itself into the very fabric of how the cell operates. So, any kind of blunt attack would be like trying to pull one thread out of a sweater using a sledgehammer. You're just going to destroy the whole sweater. The real trick is finding a weapon that is so incredibly precise, it can target only the virus's activity and leave our own cells alone.
So how in the world do we do that? Well, to see it in action, we're going to zoom in on one of the most sophisticated viruses out there, HIV. HIV is a special kind of virus called a retrovirus, and that just means it has a few extra, very clever tricks up its sleeve. That makes it incredibly tough to fight, but also the perfect case study for an absolutely brilliant solution.
You see, HIV's strategy is just diabolical. It doesn't attack just any old cell. No, it goes after one very specific target, our CD4 T cells. And these cells, they're basically the generals of our immune system. They're the ones coordinating our body's entire defense against any infection. So by taking out the command center, HIV just leaves the whole body completely defenseless.
Now, to pull off this heist, HIV brings three critical tools. Let's call them its heist crew. The first one is an enzyme called reverse transcriptase. Think of this as the forger. Here's the deal. Our cells are built to read DNA. But HIV's genetic code, it's an RNA. So this enzyme does something our cells can't possibly do. It reads the code backwards, turning the virus's RNA into a DNA blueprint, a forgery that our cells can actually read and will then obey.
Okay, so once that fake DNA blueprint is made, the next member of the crew steps up. Integrase, or the infiltrator. This enzyme takes that new viral DNA and literally stitches it right into the host cell's own chromosome. And this is a total game changer. The infection isn't just some temporary program running anymore. It is now a permanent part of that cell's own genetic code, which means it's also part of the code for every single cell it divides into.
And the final tool in the kit is Proteus, the assembler. So after the hijacked cell has read that viral DNA and produced these really long, messy strands of viral proteins, Proteus comes in. It acts like a pair of molecular scissors. It snips those long, useless strands into the perfect, finished pieces that are needed to build new, fully functional, and infectious viruses.
So there you have it. The virus's three key tools: the forger, the infiltrator, and the assembler. The absolute genius of modern medicine was figuring out that if you can just sabotage the tools, you can stop the entire heist.
And that realization, that led to the invention of antiretroviral drugs. And the strategy is just beautifully symmetrical. For every single one of HIV's tools, scientists engineered a specific saboteur to stop it. To block the forger, we have reverse transcriptase inhibitors. To stop the infiltrator, we have integrase inhibitors. And to disable the assembler, we have protease inhibitors. Each one of these drugs is designed to precisely jam the gears of one specific part of that viral machinery. It stops the whole replication process cold, all without having to destroy the host cell.
I mean, the development of these drugs completely changed the world. But, having a weapon is one thing. Using it is something else entirely. The real, true impact of these medicines isn't something you see in a lab. You see it in the real world. You see it in people's lives.
And look, nothing makes the power of treatment clearer than this comparison right here. On one side, you've got the basketball legend, Magic Johnson. He was diagnosed with HIV back in 1991. He immediately started treatment, and this is the crucial part, he's stuck with it. Today, he's alive, he's vibrant, he's thriving. On the other side, boxer Tommy Morrison, diagnosed in 1996. He denied the science, he never sought consistent treatment, and he tragically died from complications of AIDS in 2013. Two men, the same virus, two completely different outcomes, all based on a single decision, whether or not to use the tools that science had created.
So what was the difference in those two stories? It really all comes down to one single critical word: adherence. It sounds simple, but it can be incredibly hard. It just means taking your medicine exactly as it's prescribed every single time, without fail. It is the absolute linchpin that turns what was once a fatal diagnosis into a manageable condition. And believe me, the stakes for adherence could not be higher. If you start missing doses, the level of the drug in your body drops. And that doesn't just give the virus a chance to start replicating again. Worse, it creates the perfect training ground. A low dose of the drug for the virus to evolve and develop resistance, and then the medicine just stops working altogether. But when adherence is successful, the exact opposite happens. It restores your immune function, it reduces sickness, and it can even lower the amount of virus in the body so much that it becomes impossible to transmit it to someone else.
Look, the success we've had against HIV is a monumental achievement in science, but it's really just one battle in the ongoing war against viruses. The principles we just went over, finding a virus's unique tools and then figuring out how to break them, that's the core strategy we use to fight tons of other viral enemies, from something like the common flu all the way to new global threats.
And when you boil it all down, the mission for pretty much any antiviral therapy is this: shorten the illness, make it less severe, and cut down the chance of spreading it to others. Take a drug like Tamiflu for the flu. It doesn't cure it, but it targets an enzyme that the flu virus needs for that final release step of the heist. By blocking that, it makes you sick for a shorter time and less miserable while you are. The playbook is always the same: find the virus's weakness and hit it hard.
Which really brings us to the big picture here. This whole thing, this battle between us and viruses, it's a constant biological arms race. They evolve, we innovate. We come up with a new drug, they eventually figure out a way to resist it. The principles we've talked about today are our best weapons, and they're constantly being sharpened and aimed at the next threat. So it leaves you wondering, right? What's the next big breakthrough going to be? Universal vaccines? Gene editing tools that can literally snip the viral code right out of our DNA for good? The race is on. And the next game-changing discovery is out there just waiting.